previous work a little bit, but just in case he doesn't, I'll mention that we have Saso to thank for all the LZ4 compression support that's in yeah, that's a little bit popular. Cool. So now he's here to talk about some future ideas around compression. So.
Yep, cool. So I suppose most of the people out here are already familiar with my work. So I'm going to talk about a mostly new feature, because I can do it in 15 minutes. And we're going to be talking about essentially what's pointless work in compression and how to do it with. So first a quick primer on compression stuff. Compression mostly, when you look at the world of compression algorithms out there, they're mostly falling into two categories. You got the archiving guys and you got the real-time guys. So the archivers, they are mostly concerned about doing this stuff right. So they try to achieve the most compression ratio, and they're willing to trade CPU performance for that. They'll spend a whole bunch of CPU cycles looking for patterns and basically kill your machine for a few minutes. The beauty about that is, though, that they get really good compression ratios. Really good being sort of, you'll see that in a minute. And the real-time guys try to do just a good enough job, but they'll be pretty fast about it. Those are the guys down at the bottom there. And if you recognize your algorithms there, LZJB is our current default, and LZ4 is what we hope to make the default pretty soon. So why do we even bother with the real-time guys? This is why we bother. It's when you look at your compression ratio differences, which is the top bars, yeah, LZ4 does get slightly less compression ratio than something like gzip6. But if you look at the bottom bars, which is the compression, compressible data, non-compressible data, and decompression, LZ4 is pretty damn quick. So this is pretty much why we bother with real-time stuff. It's not just for crazy things like compressing memory or doing sort of a CPU to memory transfers. It's also used for actual data because the data savings are slightly modulated by the fact that we get huge performance. But the arc, and so there's a sort of middle ground, sometimes you can find it, where you trade a little bit of the performance, well, quite a bit of the performance actually, for getting slightly better compression ratios. So we have here LZ for the high compression variant, and as you can see, you get slightly better compression ratio, approaching sort of gzip levels, but you also get much slower compression of non-compressible data, and fortunately the decompression stuff is still pretty damn quick. So this is sort of a middle ground. Now, so why do we even bother with these super slow guys? Well, sometimes it's just worth it. Sometimes we don't really bother with initial CPU usage. Sometimes we are just concerned with serving the data many times. So the initial CPU cost gets sort of diluted down. And the bandwidth can cost us a lot. So it makes sense to do it right the first time around. Certain stuff even compresses super duper well. So you take your average web server, serving out tons of text files, logs, stuff like that, compresses down really well, up to and over 90%. Log files compress even better than that. However, certain workloads do not compress much at all. So pre-compressed stuff, you got your multimedia, you got your archives, stuff that's already been sort of crunched over by some compression algorithm is pretty much a non-target. And so when we do, as administrators, look at setting up compression on our data sets, what are we looking at? Initially, we look at, are we going to pay for the CPU? It does cost money, it does cost cycles, but usually we're pretty good on large systems. These things have reasonably fast CPUs and they're underutilized. The second question is, am I going to be getting something out of it? We ask that question and we try to intuit in some strange fashion, probably akin to mind reading, what our data sets can be composed of. So we try to gather whether it makes sense to turn it on. The funny thing is, we should not even be thinking about that. We should be letting the machine figure that out. for us. And the beauty about file systems is usually when you look at files, they're either one or the other. They're either compressible or they're not compressible, usually that way. So you got your text, you got your documents, your uncompressed audio, that's super compressible, and you got some stuff that's never going to compress much at all. And unfortunately for us though, as administrators, our compression setting is per file system, so there's not much we can sort of do in a fine-grained approach, usually. So we have to sort of pick and choose our battles. We've got to choose a pretty large club in order to hammer a nail. So when we look at the performance stuff, we look at what we can do something about here. So we got the compression, we got the ratios and the compression stuff and the compression performance. That's kind of lame, you know. You can't really improve your ratios without hurting your performance. Unfortunately, that's the reality. It really is just about pattern searching, and if you remember, if you keep history in mind, you look at the progression of, for example, video compression, MPEG 1, MPEG 2, MPEG 4, and so on and so forth. The higher the algorithm and the better the compression ratios that they achieve, the more they kill your CPU, which is probably one of the reasons why we're not still getting fractal compression algorithms. All computer scientists have been all about them for the last 20 years, but so far nobody's actually built a CPU capable of running the damn thing. And for decompression, it's really just grammar processing. So you get a compressed stream, which is a complex grammar of various compression primitives, and you're just trying to reconstruct the original data. The more expressive the grammar, the slower it's going to be, pretty much. So these are sort of the two areas we can understand and we cannot do much about. The non-compressible stuff, though, has its range. Why would that slow? We usually, as I said, we know per file pretty much whether it's going to compress or not. So why the hell are we spending time trying to figure out the same bit of information over and over again? We're basically compressing by block and forgetting the history of what we've been doing previously. So how do we go about it? How do we go about solving it? So there's a few bad solutions. Let's try and make ZFS recognize file extensions, right? Well, not really. I mean, how many of them are there? Anybody know how many extensions are used for MPEG files? If there's a new platform, I guarantee you they're going to make a new file extension for that. And there's some strange questions that just make this feel like a stupid solution, like, what the hell are we doing, behaving based on what the user names the file? What if they misname a file? What if they want to do bad with the file? They're just building it with zeros. Really cheap for them, really expensive for us, if they name it right. And what I don't, so the other solution there is, let's just make compression per file a property. We'll let the user decide. Yeah, good luck trying to keep track of a few million files and try setting the compression on them. There's tricks you can do with directories and stuff like that, but pretty quickly you're going to be sick and tired of it. You're just going to turn it again on a raw, which is, again, getting back to the file system setting, which originally was a sensible decision, but this is not. And of course, frequently the administrator is not even the user who's actually using the storage system. Think your average shared storage company environment. You got 500 users writing to the same X drive, and they're just cramming it all full of weird data. How do you know what's compressible or not? You're going to run shell script for that or whatever. So what we did at Nexenta was, well, why don't we just use the file system itself to track per file compression? We'll just make ZFS kind of smart about remembering what it's been doing in the past. So we just extended a bunch of the import structures. We did not modify the on-disk format, and we just have ZFS make the decision based on its historic performance. There's a simple heuristic. It just checks how often I've succeeded. If I've not succeeded much at all, I'm not going to try for a while, then I'm going to retry again, and it progressively either backs off or becomes more reluctant to stop, to back off from compressing files. The beauty about this approach is it works for any file, any data. You don't lose much compression ratio at all. So far I haven't actually seen any. And it works even for composite crap. So you take your VMD case, which is full of all manner of data, and we can sort of dynamically adapt to various write patterns going on in there. So there's a few numbers that I can show you on the performance there. There's a couple of confusing lines here, but essentially the important lines are the top one and sort of so this is compression performance with a certain amount of constant input data flowing that's not compressible. Essentially your random garbage going into your storage system. The top line there is the performance with smart compression on, which means that we completely ignore the non-compressible stuff. And the line just below that is the situation where we just turn it off and just try and compress everything. So you can see that there's about, I don't know, it's like 20% performance increase. With GZIP1, it's even greater because for some reason, GZIP1, the regular compression stuff is faster than when it gets fed uncompressible crap. So the performance difference there is much larger actually. And that's about it. I'm trying to make it fast. So questions, we talk now? Go right ahead.
When you write
So the algorithm works essentially by remembering its results. So we track the compression performance on a per block basis. When the block depends on what the state is currently off the file. So when it was hit by a lot of incompressible data, chances are we'll skip it. And we'll just account it as there's a bunch of data we tried, not compressed, and we'll try again later on. When the file has been getting a compression, we'll try and compress it. If it works out, we'll count it as a good job. If it doesn't compress, we'll count it as a no. And then there's essentially a floating statistic that will, after it dips below a certain number, we start backing off and backing off and backing off. The thing with LZ4's test for whether something else is compressible is that it is fast, that's true, but it's sort of a quick check. So it'll either determine that something's, so there's a good chance that it'll impact your compression ratios pretty severely. It's actually tunable inside of LZ4.c, how hard it should try. And the effect of that is, if you use that quick test, chances are you're going to hurt your compression ratio, which is, for example, why if you look at the high compression variant with LZ4, you'll see it's not there. It's just the non-compressible performance is exactly or almost the same as the compressible one. It's because if you do these kinds of quick checks, chances are you'll throw away data that you could have compressed. It's unfortunately a trade-off. But the beauty about it is, about the smart compression approach, is that we don't even have to do that check anymore. We can remember our previous performance. That's the point. The compression algorithm can be stupid.
Needs to be a monkey in the wrench, but have you ever heard of the quality assurance sample techniques used during cycle 1?
I wasn't alive then.
You're talking about sampling methodologies. In the Second World War, they had to figure out what was good, what was bad, so they did batch analysis. They couldn't sample everything, so they developed statistical methods, and they used what were called charts. They just pulled a bunch out, did some tests, based on the results, either increase the tests or they reduce the tests. Based on those tests, they change their process of manufacturing. That sounds a hell of a lot like what you're trying to do here.
Possible. Yeah, you're going to have to read up on that. Thanks.
You said there were no context changes, so does that mean on a reboot you start relearning?
Sorry?
You said that there are no context changes, so does that mean on a reboot, after a reboot you start relearning everything?
Yeah, it will, not only will reboot, the default currently for that thing is on, for that feature. So, yeah, there's no persistent changes in that we do not modify on this estate. There's one property we add, which is sort of not really changing on this estate, it's not incompatible. And it'll turn on automatically if you have compression turned on the data set. So it's sort of a separate setting, but by default it's on. When you do use compression on your data set, you're going to get this feature automatically on. In the DDoM. And yeah, so if all the applications that had that thing open close it, we'll lose it. But you know. Okay, thanks.
Just one more